the task is basically to compute the state transition matrix, and that is what this lecture is about. Let us see what are the different techniques or different approaches to compute this state transition matrix. The first one is our very familiar Laplace transform and inverse Laplace transform. So this is very easy to understand, that if you consider the homogeneous system x dot equals to Ax and you take the Laplace transform considering the initial condition. So then what you will get, so with some manipulation you will get this, and you will have xs equals to si minus a inverse x0, and your xt would be the Laplace inverse of this. It is Laplace inverse of si minus a inverse x0, and we know that xt basically will be e to the power of at x0, and hence we can be very sure that e to the power of at is nothing but Laplace inverse of si minus a inverse. So if you are given a matrix A, suppose a matrix maybe a third order matrix like this, I am taking a very simple one so that I know the eigenvalues. So maybe this 3 and 2. So the eigenvalues are 1, minus 1 and 2, and you can compute si minus a, and that would be your s minus 1 0 0 minus 2 s plus 1 0 0 s minus 3 s minus 2. So now you have to calculate the inverse of si minus a, and if you remember, I think there was this Levery's algorithm. Levery's algorithm was there to help you calculate the inverse of si minus a, so that you can apply to calculate this, or you can go about in the normal manner to calculate the inverse of si minus a, and you will get something, and you have to do a Laplace inverse over that. So you have to do a Laplace inverse over that, and what you will get a matrix phi t equals to e to the power of at. You will get a matrix which will be a 3 cross 3 matrix, and these terms would be some functions of time, f11, f12, f13, like this. Some functions of time you will obtain. So here also f21 t, f22 t, like this. So like this you will get some functions when you do the Laplace inverse. So when you will get the actual problem, then you can go about doing this and you can see what happens. The next computational way is to go by the method of diagonal forms and Jordan forms. So let us first see the diagonal form. So when we have the diagonal form representation, we know that we can, if you know the eigenvalues, you can diagonalize the matrix, you can diagonalize the state space representation. So you will get the diagonal form, and this matrix P is basically the modal matrix, where all these V1 to Vn are the eigenvectors of the corresponding eigenvalues. So you can find this out, you can find your M. So you would be able to have your M with you, and your lambda, capital lambda, which is the diagonal form with you, and M inverse would also be, you will be able to calculate if you have your M with you. So now we need to find out the state transition matrix. The state transition matrix in the diagonal form is very easy to compute. It is nothing but simply e to the power of lambda 1t, lambda 2t, etc., etc. in all these diagonals. So whatever is the eigenvalue in the diagonal, you just raise it to the exponential e to the power of lambda t, you just do that. So for lambda 1 it is e to the power of lambda 1t, for lambda 2 it is e to the power of lambda 2t, simply like that. So it is very simple. So this can be directly computed. So the e to the power of capital lambda t, which is the state transition matrix in the diagonal form, that can be very readily computed. And once this is known, you simply have to, what is your job here? Basically your job is to basically find out the m inverse and do this computation to get the e to the power of at in the original, the state transition matrix in the original state space representation. That is what you need to do. So the computation basically boils down to figuring out your m, which is very easy to find out because the eigenvectors are easy to compute using the column operations, or sometimes by direct observation you can figure out what the eigenvectors are. So you will be able to find the eigenvectors, you will be able to make the matrix m. Now m inverse will take some time, but if you calculate it cautiously, you will be able to get m inverse, and then you can find out e to the power of 8. So this is one way. So this is for diagonal form. Now suppose you have the Jordan form representation. That means you have possibly repeated eigenvalues. Then what happens? Your Jordan form is basically the Jordan blocks coming in the diagonal. Instead of the eigenvalues, these are the Jordan blocks coming in the diagonal, and this basically is the same. So when you have e to the power of jt, you have e to the power of j1t in the j1t, e to the power of j2t, likewise e to the power of jkt in the diagonals. Okay. Now in the same manner you have this relationship, and what is your modal matrix m? You know, these are the set of generalized eigenvectors. This you know now. Generalized eigenvectors you find out. So some eigenvectors are giving rise to this j1 block, then some set of eigenvectors to j2 block up to jk. So this, you know which blocks correspond to which eigenvalues. In that order you should place the eigenvectors, you should not jumble things up. So you get your modal matrix m. So you get m, you get m inverse. So m is nothing but p, m inverse is nothing but p inverse. So you obtain those, and you have your e to the power of at. But here one question is this: what is my e to the power of j1t? Right, because my j1 is not simply a diagonal element, it is a block. So suppose we have lambda, it is like this. Suppose it is a block of size 2, if it is a block of size 3, then it is like this, and it can be larger. So what is basically then e to the power of j1t, and as a matter of fact any jkt. So let us see. So if you have a block jk where we have so many repetitions, suppose it is r times repeated, the eigenvalue lambda k is repeated r times. Okay, so this is a r cross r block. So this is a r cross r block. So now your e to the power of jkt is nothing but e to the power of lambda kt taken out of the matrix, and this is the r cross r block. And you see what you have here is 1, then t, then you extend this t square 1 by 2 factorial t square, and likewise you go on till you will actually go on till r minus 1, because there are r number of terms here. So this would not be r, this would be r minus 1, e to the power of r minus 1. So this term would be this. So you go till here, and in the next row, this entire thing is getting shifted to the right. So your last term would be basically r minus 2 factorial to the power of r minus 2, and this is getting shifted and a 0 is getting added in the left. So as you go downwards, more number of zeros are getting added to the left and the entire thing is getting shifted. So at the very last but one, you have t at the t as last entry, and all the others are zeros, and the last but one would be 1, and in the last row all are zeros except the last being 1. So this is the matrix. Remember that e to the power of lambda kt has been taken out. That means this is getting multiplied with all these elements. Okay, this is a general statement I have written down. So the ith row will have elements t to the power of I minus 1 by I minus 1 factorial, with I from 1 to r minus I minus 1. So if it is the ith row, suppose it is the second row, then it will have from t to the power of 0, which is the 1, to the power of 0 will become 1, and it will go till r minus 2. So I is 2, so you will have r minus 2 minus 1, it will be simply I, it will not be I, it will be simply I. That was one mistake. So r minus I, so it will be till r minus I, and starting from the diagonal element. So the diagonal element will be 1 always, and starting from that you will go rightwards till r minus I number of terms. So when you are in the r minus 1th term, you are only having the if you put I as r minus 1, you will again get 1. So you have only as one single term. Okay, and uh, so this is 1. This is the r minus 1th block. So it starts from 1, and then you would have t to the power of 2, t to the power of 1 you have to have, right? So yeah, so r minus I would be r minus r minus 1. I think it would be so your last term, your first term would be 0, that is always you would have 0 as your t to the power of 0 as your first term. So if you start from I, in the first row it must end in r minus 1. So if you have I ranging till r, then it's fine, and in the last one it would come to r minus 1. So you have I equals to r minus 1, I'm suddenly confused here, so maybe it is r. So you have r to r minus 1. No, I think this is fine. R minus, this is the ith, this is the first row, so it would go till till r. So it would go till t r minus 1 by r minus 1. Then in the second row you have I as 2. So your span is from 1 to r minus 1, and when you have r minus 1 put as I here, it is till r minus 2. In the r minus 1th row, your I is r minus 1. So what you get here is basically r minus r minus r plus 1 plus 1. So you have 2. So you have 2 here, and t to the power of 2 minus 1 is 1. So this is fine. So it would be I minus 1. Yeah. In the last row, it is in the last row I is r. So you have 1 to 1. So it is only 1. That is fine. So this was wrong only. So this is right. This is correct. So this is how you can compute for the Jordan block also. This is very easy, not so difficult. It has a form, so you can directly write down that form, and once you have write down the block, so every block you can actually find out. So depending on the size of the block, you can compute this e to the power of j t, these things, and finally you can figure out what your e to the power of a t would be in terms of e to the power of j t. So this is about computation in the Jordan form. Now there is the last one. The last method is the Kelly-Hamilton's theorem. The Kelly-Hamilton's theorem is this, what you read in the italics. It is very important. I guess at one point of time in our lecture I stated this theorem once. So this is the Kelly-Hamilton's theorem. It says that any function of the eigenvalue lambda of a square matrix A is satisfied by the matrix itself. So now if we have any polynomial function which is a function of the eigenvalue lambda, then it can be, that polynomial function can be represented as a sum of terms with the highest order of lambda as n minus 1, and there are no further terms. So this is a n number of terms function, a polynomial function with n number of terms with the highest degree of lambda as n minus 1. This is a direct implication of the Kelly-Hamilton's theorem. How? See, the characteristic polynomial p lambda is what? It is some lambda to the power of n plus a1 lambda n minus 1, like that it is going on till n minus 1 lambda plus an equals to 0. So that means you can express lambda to the power of n as some terms with as a sum of terms with I equals to n 1 to n. So n number of terms. So you can express lambda to the power of n in terms of n number of terms with the highest degree as lambda n minus 1 minus, correct? So if you have any polynomial where you have other terms here of lambda to the power of n or n plus 1, like all these things. So suppose you have a term with n, then you can replace this with this, because this is always true. So you can express lambda to the power of n as a sum of these terms because of the characteristic polynomial. So you can replace this lambda to the power of n with terms containing powers of lambda starting from 0 to n minus 1. If you have a lambda n plus 1, So here if you do lambda n plus 1, then you will have this and that means there is a lambda n coming in. So when I equals to 1, there is a lambda n coming in, but that lambda n again can be represented as a sum of these terms. So any higher power of lambda starting from n, n plus 1 and higher, all these higher terms, higher powers of lambda can be expressed in terms of these lower powers. This is because of the characteristic polynomial. And that is the reason why any polynomial function of lambda can be represented by only terms from lambda to the power of 0 to lambda to the power of n minus 1. And since this is satisfied by A, that means this is also true. So if there is a function, lambda which we know is if there is a function which we know is satisfied by the eigenvalues of the matrix A, we can write that function in terms of as a polynomial function like this, and the matrix A also satisfies that same function. So now we utilize this fact to see that if my function is the matrix polynomial, then it is satisfied by the eigenvalues. So e to the power of lambda t would be this, and this is satisfied by eigenvalues lambda 1 till lambda n. So you will get n number of equations, and how many unknowns you are having? These alphas are unknown. You have exactly n number of unknowns. So you can basically solve for alpha 0 to alpha n minus 1. And when you have solved for alpha 0 to alpha n minus 1, you will find out that these are basically functions of time, and hence you will get your e to the power of a t directly as this. So here these are functions of time. So it looks like a constant term. It looks like addition of constant terms, but it is not constant. The alphas are functions of time. So that's what makes the matrix exponential also function of time, which is what it is. Now there is something to note here, that it might be so that we have repeated eigenvalues. So in case of repeated eigenvalues, what we do, we take derivatives of f lambda. So if you have n number of repetitions, you have to take n number of derivatives of f lambda. So this is f lambda. So you take a derivative, you will get lambda e to the power of lambda t equals to alpha 1 plus 2 alpha 2 lambda plus 3 alpha 3 lambda square plus uh, alpha n minus plus n minus 1 alpha n minus 1 lambda n minus 2. So you will get this, and if you have another repetition, you have to do another derivative. You have to take lambda square e to the power of lambda t equals to alpha 2 plus 6 alpha 3 lambda plus, like this you have to do. You will have here n minus 2 n minus 1 alpha n minus 1 lambda n minus 3. So you will get these equations. Now you can put your lambda value and you will get distinct equations coming out. Now you can solve for all of the alphas, and then you will get your e to the power of at also, after knowing what your alphas are. So this is another method of solution. So you have to learn all the three methods. You have to practice in all the three methods, and if the question asks to apply one particular method, you have to apply that only. if the question is relaxed in not being specific about a method, you can apply any one of the method which you find yourself to be most comfortable with. What we generally find while working, we would find that the diagonal form is the most easy one to actually work with. So normally we would go with that. So this here we have the end of the lecture, and I guess I can show perhaps a quick example maybe with Cayley-Hamilton's theorem. Let us see. So that same matrix, or maybe a different one, 0 0 2 minus 1 0 0 3 and 2. So here we know the eigenvalues are 1 minus 1 and 2. So the polynomial is, do we need the characteristic polynomial? We don't need the characteristic polynomial, right? So we can formulate the equation e to the power of lambda t equals to alpha 0 I, no, not I, sorry, alpha 0 plus alpha 1 lambda plus alpha 2 lambda square. So that is all that we need, because it is a third order system, so it is still 3 minus 1, which is 2. And now we put your lambdas. So you have these equations: e to the power of t equals to alpha 0 plus alpha 1 plus alpha 2. Then e to the power of minus t equals to alpha 0 plus not plus, minus alpha 1 minus alpha 1 plus alpha 2. E to the power of 2t equals to alpha 0 plus 2 alpha 1 plus 4 alpha 2. So now you have your set, and what you have here is this: e to the power of t, e to the power of minus t, e to the power of 2t, and you have a matrix here 1 1 1 1 minus 1 1 1 2 4 alpha 0 alpha 1 alpha 2. Now you have to solve. So if this matrix, you call this matrix as some matrix, say some matrix, say q. So then you have your alpha 0 alpha 1 alpha 2 as q inverse of e to the power of t minus t to t. You get your alpha 0 alpha 1 and alpha 2. Now then you can say that your e to the power of at would be this, simply this. So that is what you need to go through. So this is the steps that you need to go through. So you can also find out your alphas by simply doing some manipulations in these equations, but if there are large number of equations, it is good to form the matrix and do the matrixing. But for very simple relationships, you may try to find alpha 0 this very directly. Maybe you can compute very directly. So that is all I wanted to say about the theoretical part of this lecture, and when you get the examples and the tutorials, you can go through those. You can try to do this on your own. You will be able to find out the examples, and you'll be able to solve this. You just need to be a bit cautious and attentive while doing the solution. The steps are very clear what to do actually. So with this I end the lecture. Thank you for your attention.